Hello and welcome. Eamonn Darcy is my name. I'm the founder and operator of Qbism, the Quantum Education Centre of West Australia. So please subscribe to the channel if you can and like the video. It does make a difference. Now already we're up to video lesson 4 out of a series of 10 10-minute videos. So we find that 10 minutes is a good time for somebody new to this knowledge of quantum physics and quantum computing. 10 minutes is a good time that you can stay with it and understand what's going on. And because it's only 10 minutes, I obviously can't cover the whole topic, but what I do is introduce you to the exciting bits. So hopefully it's working well. Okay, let me start my timer. 10 minutes starts now. So here in lesson 4, we're going to cover linear algebra, the basics of it. And I think, given again the 10 minutes, I think what I want to really get over to you is why we need to use linear algebra in quantum computing. Because when you understand that, then you make a decision whether you want to invest the time into learning linear algebra, which you're going to have to do, especially if you're going to do any programming in quantum computing. But just to understand what's going on is important. So I'll take you through the basics of matrix multiplication. You know, it really just what are rows and columns and how you can multiply two matrices together, which of course you're going to have to know. So what is linear algebra? Now, to go into everything about linear algebra is outside the scope of this presentation, but I really want you to understand how we can manipulate the quantum state of a superposition that you previously learned. I want you to understand how linear algebra can do that. And it may seem like learning a lot of formulas and things, but it will eventually make sense, I assure you. And if you are going to go on to do some quantum algorithms, then you really are going to have to know and understand the subject. Do you remember superposition? I think it was in fact, it was the very first lesson that we did. And just to recap, that's where a subatomic particle is in this strange state of superposition, of wave-particle duality, where it's a wave and a particle at the same time. It is in a state of reality that we don't find in our normal world. And the Bloch sphere is the way that we can refer to it. So in a normal computer, you've only got 1 or 0, and if the state is on, you have a 1, and if the state is off, you have a 0. So in a traditional digital computer, you've only got 2 states, on or off. That's all that can be referenced to, recognized, and then manipulated. What we call, and what you're going to really, I'm going to talk about a lot today, state transformation. So all digital computers rely on the binary code. So you've got states being transformed into other states merely by knowing whether the first state, or the state you're multiplying it by, is in on or off, 1 or 0, whether there's a current going through the transistor or there isn't. That's all you've got in classical. But in quantum, because of superposition, you've got almost an infinite number of states which we can manipulate, and I'll get onto that as well. But it's a lot more complex than multiplying just 1 and 0 by 1 and 0, and then what's called concatenation. So putting all the 1s and 0s together to make a bigger number, and then multiplying that by a bigger number. And believe it or not, all the computer systems that we have today, all the amazing things that you can do are based on that. Whereas a quantum computer is, the quantum state can be almost an infinite number of different states. And that's what gives it its exponential capability. 4 minutes left. So again, before measurement, the subatomic or quantum particles in a state of superposition. Remember, as soon as you measure it or you try and know or observe or understand more about the state, it collapses to either 1 or 0. It becomes the same as a digital computer. So how can we manipulate it? And if you look at those 3 bottom sentences, that describes what quantum computing is. 1, we can manipulate the quantum states of the superposition physically by firing varying strengths of microwave pulses or bursts for different durations at the superposition. That's how we can physically control the state of the superposition. Now, we visually can represent those states by using quantum notation, which we'll be getting into, which gives quantum gates and quantum algorithms. However, to calculate and interpret those quantum states, we use linear algebra. 2 minutes, 45 seconds left. So again, I don't mind saying this point many, many times. If you think of the Earth, you can have, in the classical world, you can only have a state at the North Pole or the South Pole and nothing in between. And it can be a 1 or a 0. Whereas in the quantum Earth, we can actually access and map to every single location on the Earth. In this example, I was using an A4 piece of paper. On the classical world, we can only have 2 A4 pieces of paper. But here we can locate A4 pieces of paper throughout the whole globe, and we can refer to them and multiply them together by using linear algebra. Now, the process, one of the main things you need to know, of course, is matrix multiplication. So what's the first state? What's the second quantum state? And multiplying them together will give you a third quantum state. And I've got 1 minute 26 left. There are 2 rules you need to know. Rows come before columns. So if I said to you, it's a 3 by 4 matrix, that means it has 3 rows and 4 columns. I can remember it because my name's Darcy, D-A-R-C-Y. So the R comes before the C. That's how I remembered anyway. And when you multiply them across, what you actually do is to multiply 2 matrices, you multiply the first row by the first column. And here's a little table that shows you, although visually it's quite easy to follow. You're just multiplying the rows by the columns and putting the result in the third matrix. And the dimensions have to be in a certain order. But basically, it's that easy. If you look at that example and look at these what and multiplying every time to give the result to create the new matrix, that's how powerful it is. It really is. Well, that was very quick, so thank you very much. But I'm going to now for video lesson 5. Oh, and there goes the timer. So thank you once again. Please remember to click the links to the other lessons. If you can get through these 10 lessons, you'll find that you're an awful long way towards learning quantum computing. Thank you very much indeed, and I'll talk to you soon. Bye now.